Good morning, everyone. When I was preparing for this presentation, I was a bit worried about the topic. So everything here seems to be very code-oriented, a lot of C++, a lot of Python, a lot of best practices. And I'm here to tell you a story. So for something a bit different. So this is a story. It's like a roller coaster ride. And first of all, I have a disclaimer for you. This is when you think about success, you think about going from A to B, and you plan that you're going there straight ahead, and there's no bumps in the road or anything. This is not that kind of story. This is going to share with you all the challenges I faced. So when working on this project, what started being a tiny little project that I would end up writing a thesis about, it ended up teaching me so much, and I faced crossroads, and this is a story about what I did to overcome them. So hopefully by the end of this talk you managed to get something out of it. But again, I must say I don't have a silver bullet for you on how to make your clouds trusted. So getting that out of the way, once upon a time there was me, young and naive and looking for a project to work on. So I found this very nice research team in Nokia Bell Labs, and I found my supervisor who proposed this topic. Do you want to work with an obscure piece of hardware and the cloud? And note that at this point, I knew the cloud was someone else's computer. So I didn't know many details either about the obscure hardware or how the cloud worked, but I like challenges. So I thought, well, why not? Let's dive into this. So first, I'm going to talk a bit about the background, so the basics you need to know to understand trust and cloud. So bear with me for this theoretical part. So the cloud, for real. The cloud, we can simplify it and think about it as you have a hardware layer, so where you have all your hardware resources, so think computing, networking, storage. And on top of that, you have a virtualization. Of course, so you have the hardware, and then you have the firmware for each of those machines. You have the operating system that runs on those machines. And on top of that, you have the hypervisor, so the virtualization layer. The hypervisor's responsibility is to take all these hardware resources and make them available to a top level, the virtual machines. So the idea of the cloud is that it's very easy to deploy virtual workload on generic servers, and the virtual machines don't really care where the resources are coming from. So you have many industries that are moving to the cloud. So you have the telco cloud, of course. You have so traditionally you had network functions, so you had these things like firewalls or switches or base stations that needed very specialized hardware to run. So every time you needed to upgrade these, it was maybe a bit tricky. Now we have this thing called network function virtualization, which is the telco version of the cloud, and we can deploy these network functions in a virtualized manner, and then it becomes much cheaper. And other industries are doing the same. So you have medical industry taking their systems into the cloud and maybe having a bunch of IoT devices, so all these fitness trackers or even like pacemakers or insulin pumps and so on. And you have industries like automotive that also have systems running the car, running in the cloud, monitoring your car, and so on. And I use these two as an example because these are very critical systems in the sense that if these systems fail, they could cause death. So this kind of motivates my research. How do we know what state our systems are in? So one thing is you want the underlying hardware or platform where your virtualized workload is running to be in a known state. You don't want anyone tampering with it. You certainly don't want any malware in there. And one thing why this is important is, let's think back to when there were the Snowden revelations. You had our nice friends from the NSA were tampering with Cisco's supply chain. So you had Cisco, they built the routers, they put their firmware in there, and they sent them to the customers. So the thing is, somewhere along the way, our good friends at the NSA came over to the DHL officers or something, knocked on the door and said, hey, can we take those boxes of routers for a second and go into this back room? And then they would replace the firmware for a backdoored firmware and repack them, carry on, go on to your customers. And this would go undetected because this would be a modified version of firmware that would still report, I am the correct version. And if you're just looking at a version number, how do you know really what is running your system? And similarly, there's a lot of supply chain attacks. So the attackers try to get ahead of you and attack you while you're in the supply chain, because you place your trust in the third party that provides you your hardware, your software, your firmware. And that is a weak point. If the attackers can somehow get access to that, then they can run in trust mode. They can do whatever they want. And most recently, there was this big hack, the Bloomberg report on China having a tiny little chip infiltrated in super microboards and spying on great big American companies. And turns out that this is probably fake news. But the thing is, why I mentioned this is because when this came to light, a lot of the technical experts just said, well, there's not enough. Although this is, well, I guess technically possible, there are so many easier ways to do it right now. Firmware and software is so bug-ridden, or there's easier ways to attack the supply chain that maybe you wouldn't go all the way down to the hardware level. So what I want to emphasize here is that we want to know, as well, Nokia sells these like cloud solutions, so we want to guarantee that our systems are not tampered with. Our hardware is in the correct known state, and we trust them. And what I mean by trust is that we guarantee that the integrity, nobody has tampered with the integrity of our software or hardware. So if we go back to cloud architecture, we have the virtual workload. In order for that to run, it needs to trust all the underlying layers. So the virtual workload needs to trust the hypervisor, which in turn needs to trust the operating system. So need to trust it in the sense that you can only guarantee it works correctly if nobody has tampered with it. So how do you know you're in a good version? And we can build this chain of trust all the way down to the hardware. And one way of guaranteeing this integrity is using code signing. So you take your you take your firmware and you take your software, and you only used signed versions of these. So you place your trust in a third party that tells you, hey, don't worry, this is good code, this is good software, you can run it. But the problem, I argue, with code signing is that if you go to the dark places of the internet, then you can find some stolen certificates that you can use to sign your own malware, or you have a bunch of supply chain attacks where attackers hijack other companies that develop this software, and you can effectively get your malware signed. So I argue signing your code is not enough to guarantee I know the state of your computer. So if I ask you here, how many of you know what exact version of your BIOS is your laptop running? Okay, one of you. Nice. How do you know it's that exact version? Have you looked at the BIOS and read the number? Dump the contents. Okay. But did you know that some modified BIOSes can make it so that if you ask it to dump the contents, okay, good. Then you're going the right way. So you want to know what is running, and you want to make sure about that. And there's this very little tiny device that can help us with this. So this is a trusted platform module. It's a really, really tiny device that's available in most server class hardware nowadays. In some laptops as well. I think mine has one. A lot of the corporate laptops have one. And the nice thing about this piece of hardware is that it's a little chip that's embedded in the motherboard. It's tamper resistant, and it has very nice functionality. So it provides secure storage. In a TPM, it talks to so it's a discrete component that talks to the CPU through I/O, so like a serial bus. And it can provide secure storage that's tamper-proof in the form of a set of registers that we call platform configuration registers that we can use to store hash measurements. So from now on, whenever I say measurements, I mean hashes, cryptographic hashes. And you can also use, it comes with non-volatile RAM that you can use to store whatever you feel like. Additionally, it can perform cryptographic functions. So it can create keys, it can encrypt, it can decrypt, it can sign. So it has some kind of cryptographic functionality on board of the chip itself. And it also has a notion of a unique identity. So each one of these devices at manufacture time, they get two key pairs, an attestation key and an endorsement key. And these keys are unique. There's no single other TPM in the world that will have the same keys as you. So we can form a strong identity for each of these devices, which would in turn give a strong identity to a machine that has a TPM. And finally, they provide a mechanism called quoting. So if you take a machine that has a TPM, you can ask the TPM, can you give me the values of your measurements? And it'll provide those measurements, and it'll sign those measurements. So you can always guarantee that measurements are coming from your machine. So we use this device to build a boot chain or trust chain when our machine boots. So if we can somehow, when our machine is booting, we can measure each of the components in the boot sequence before they run, we end up with this kind of trust chain all the way from the time your machine boots. So you have a machine with a TPM. Your machine boots, and the first code that runs, and this is the process at least for x86 machines, the first piece of code that runs is the CRTM. And this is the core root of trust measurement. It's a little piece of code that what it does, this is our trust anchor in the system. So it measures itself, it takes a hash of itself, and it stores these measurements in the TPM. And before it lets the BIOS run, it'll measure the BIOS, store the measurements of the BIOS in these platform configuration registers, and let the BIOS run. And in turn, the BIOS will do the same for the bootloader, and the bootloader will do the same for the kernel. And finally, at runtime, you can take measurements of your file system and store them in the TPM. So a nice thing about these registers inside a TPM is that you can't directly write to them. So you can't just call, please write number 1 to my register. You always have to extend them. So what you end up doing is you take the value that's in the register and you extend it by concatenating the new value you want to add, so your new measurement, and you hash this. So effectively you're kind of building a Merkle tree of measurements. Then when the machine is all booted up, you can request these measurements and they will give you a snapshot, or they will explain what was the state of your platform after it was done booting. So at this point we have a device that allows us to do secure storage, and we have a way of measuring the components in our boot sequence. So how do we know if this is good or bad? So right now, I just have a bunch of hashes. There's this process called remote attestation, where we place a server. So we have a golden machine, a reference machine, with all the good configurations you want. Then you store these in a database, and whenever you have to check all the other servers you configure. So you have a challenger that will ask the attestation server, hey, can I trust that machine A? And the attestation server will go and say, hey, please, A, can you give me your measurements? To which the machine A returns the measurements, and it does a comparison. So these values match the good values I already know. And if they do, congratulations, your machine A is trusted. So once we got this out of the way, we have the problem that doing this for a single machine is quite easy. So you build a reference. You don't even need to build a reference machine. You know your measurements. But once you have many more machines, it starts to become a challenge. How do you monitor hundreds, thousands of machines in a data center and a lot of devices? And I mean, you can also extend this to the edge of the cloud and all the IoT devices. So if you want to guarantee trust all over the ecosystem, this becomes a bit challenging. So this is what I set out to do. And I had understood the theory. I knew what a TPM was now. And I had an idea of what I wanted to do. I had looked at the state of the art. And I thought, well, I'm going to make this better. I'll build my own attestation server. So I set myself with a master plan. And I figured, well, I'm going to focus first on solving the problem at the platform level. So at the hardware, very lower level at the hardware, I want to guarantee that everything running in the servers is in known good state. So I thought, well, I'm just going to focus on this part and add an attestation server there that I'm going to build. Then I came up with this master plan. And now in this talk is where I get to the more interesting bits now that we got all the theory out of the way. I'm going to talk about how... So when I started this project, I thought, well, it's a bunch of components. I individually understand what each of them do. How hard can it be to just piece them together? And so I started working from the bottom. I think, well, I'm going to create a server. I'm going to use Flask. And then I went to what I thought was the most important decision in my project. Should I use Python 2 or Python 3? So at least that's what I thought was the most important decision of my project. When I started building it, I take a look first at the very lower layer. So how do I get a server. It has a TPM. How do I turn this device on? How do I find it? And this was actually fairly easy. You just go to your BIOS, and you have a little option that you set to enable. There you go. You have a TPM. Is your machine secure now? Well, turns out it needs a little bit more of work. So if you want to talk to the TPM, you need this kind of a software stack in order to get all the libraries to communicate to the TPM. And the TPM is defined by the Trusted Computing Group. And recently they defined like a new version that breaks backwards compatibility. So the development of these libraries is quite fast-paced and it's ongoing. So it's quite a challenge to work with a software stack. So all of these, so the libraries you use to talk to TPM, it's 3 main projects that are hosted on GitHub. So I think they're developed by people from Intel and some other contributors, so it's open source. It moves really, really fast, and it seems like people are still kind of trying to figure out how to make your libraries compliant with the standard. So the first lowest level of the components is the TSS. These are the set of libraries that allow us to send a command in nice language, so command in C, and it turns it into something that the TPM understands. And when the TPM replies with bits and bytes, it turns that into something we can use in code. On top of that, we have the ABRMD, which stands for, I'm sorry for the abbreviations here, really, Access Broker and Resource Management Daemon. So you have to create this kind of daemon. The TPM has no idea what's going on top of it. So you have to create a daemon that tells the TPM when to do context switching, when to load things into memory or out of memory, and someone who manages how to let processes access the TPM or not. And then the important part is the TPM tool. So as a user that wants to build applications that use the TPM for something, these are probably the tools that you end up using. So it's a set of command line tools that you can use to issue commands to a TPM. So very nice. So I set myself to installing these. And I thought I could go sudo apt-get install tpm2. Turns out you can't. So there's still one of the problems with working with this kind of very new library that's still being developed is just there's not enough people maintaining it, so there's no packages for the main distros. So you have to go and build it yourself, which is, well, that's fine. You go, you get all the dependencies, you clone the repositories, you run bootstrap, configure, make install. Problem is, then it becomes for you as a developer quite more work than you bargained for when you have to figure out what the dependencies are for building these tools, because there's no page saying these are the packages you need. And then the name of these packages change if you use, so I was using Ubuntu, and as soon as I changed to Fedora, then all the packages were named differently, which was a challenge, not because it's hard, but because you're wanting to build something on top of this and not wanting to bother yourself with the little things as figuring out dependencies. So one thing I learned about working with these projects is that, well, the master branch moves really fast. So I was trying to build a server that uses these tools and try to build my application logic on top of it, when all of a sudden I think I was at work and there's this little command called TPM to PCR list. So what this does is that it asks the TPM, hey, can I get the contents of your registers? And as you can see, this is a YAML formatted output, and I was just using Python, so I was using the YAML parser. I would parse this into my program and then compare measurements. Very nice. Up until one of my coworkers updated his machine to use the latest master version, where they made a teeny tiny little change. So now everything's capital letters, and since these are hex values, let's add 0x in front of it. But it turns out, when you go and tell the YAML parser, please parse this, this gets automatically interpreted as really, really, really large numbers. So the challenge here is that you're trying to build some application logic at a higher level, and you want to trust that your libraries work as they say they do, but then you can't just follow latest commits because it moves so fast. Then you're constantly putting out fires in your application, never get to actually do the research you want to do. So then I had the opposite problem. What happens when the releases are too slow? Because at this point I had said, well, I'll just work with the latest stable release, and I won't update until I see other people saying it works and I can test that nothing breaks. Remember I said there was this non-volatile memory? So one thing I was doing is I was saving some configuration information in this non-volatile memory. So one day I was doing some tests and I was trying to write hello into a piece of the memory. And I kept seeing it looped, trying to write data of size 0. I started wondering, well, hello is not size 0 data. What's going on here? So it turns out you have to go and dig in the standard that it says a TPM has to report this kind of capability. So it reports what kind of so what manufacturer it has, what vendor it comes from, what's the firmware version, what kind of cryptographic things it can do. And among these things, it reports a buffer size, the maximum buffer size for writing to memory. So some TPMs were implemented in such a way that this capability was not defined. Then the code in the libraries, it thought, well, if it's not defined, it must be 0. So every time I tried writing into memory, it would think, since my TPM had this fault that it wouldn't report what its buffer size was, I couldn't write anything to it. Fortunately, we got a patch for that, so we went to the mailing list, said, we're seeing this, what is happening, does anyone know? Somebody said, oh, I was actually having the same problem. I had a patch, but I didn't release it because, well, I thought no one else would have this problem. And then they go and they make a pull request, and it gets to master branch. But it doesn't get into the release until they release the next time. So then you're stuck having to patch your software manually and keeping track of that until you can update to the next release. And again, these are kind of things that if you would be working with a stable, mature library, maybe you don't have to worry about that much. Which leads me to the interaction with the TPM community. So it's not that big of a community. There's not that many people using TPMs for doing remote attestation. So a lot of people, so there's BitLocker, I think, uses TPMs for doing disk encryption. So they just use it to save some keys. But using TPM in this remote attestation way, it's not that popular. So my source of information was limited to the mailing list, which itself, it's not a very not a very old mailing list. It's only set up from 2017. So it's quite a small user base, and you have two kinds of users. So you have the developers who are on the list because they're trying to make the libraries compliant with the standard. So their worries are different from me, than I'm a user. I just want the libraries to work as I expect them to. So a lot of the messages on the list are, hey, I'm trying to compile the tools, but they're failing. What do I do now? So it's a bit of a challenge navigating this mailing list, trying to find something useful. Because then again, you can't go to Stack Overflow, Stack Exchange, or you won't find a tutorial on YouTube saying this is how you use the TPM. So I was very happy that there was at least one mailing list I could go and contact. But it was one of the challenges. So sometimes even the people in the mailing list didn't have the answers to the questions. So working with this kind of obscure hardware was problematic because of that. Then continuing with my master plan, I went one level up, so I had the TPM enabled. Now I could talk to it and get something useful. I wanted to get measurements at the file system level. So one thing is, up until now, I had talked about a measured boot chain. I wanted to get measurements during the life cycle of my machine, so I turn them on, and let's say I have important configuration files for whatever I'm running on my machine. Let's say I'm running OpenStack, which is one of these cloud implementations. So all the configuration files for OpenStack, I wouldn't want anyone to tamper with them. So I wanted a way to detect if my files changed, how would I know they had been tampered with? So I used this integrity measurement architecture, which is it's a kernel submodule. That's what it does is it introduces this nice little hooks in the kernel, so that every time you read a file, you can introduce a hook so that it gets a hash measurement of the file and it stores it into a list of measurements. And on top of that, if you have a TPM, you can store a hash of the list of measurements in the TPM. So you can move that to secure storage, so some kind of checksum or integrity value over your list of measurements. So what it does is IMA has these kind of policies where you can tell it, these are the files I want you to measure. So one thing it uses is it uses one of these Linux security module. It uses SE Linux, the security enhanced Linux. This is originally meant to do mandatory access control in Linux, and the way it does is it adds very nice tags to your files. So with IMA, you could tell it in the policies, anything that's tagged with measure, please take a hash whenever anyone tries to use this file, read it or write it. So the way it goes is that you have your important config file. Anytime any process tries to read or write to it, you will add a new measurement to the list. And every time this list gets updated, the TPM, one of the PCRs in the TPM, gets updated. So now effectively at runtime, I can keep track of the important files I don't want to change. So that was very nice. The only challenge I faced with this was that I was working with Ubuntu, which has the integrity subsystem compiled. Automatically, it's a default value. But it does not use SE Linux. It uses AppArmor, which I've learned it's not very compatible with SE Linux. So one thing I tried was, well, turn off AppArmor. I want to use SE Linux. And then the computers came back at me with a kernel panic. So after banging my head against the keyboard and not getting it to work, I said, well, I'll move to a system that has SE Linux. I tried doing it in Fedora. SE Linux worked wonderfully right from the beginning, but it turns out the integrity measurement architecture is not enabled by default in the kernel. So then that led me to learn how to recompile the kernel so I could change 2 lines. That was a learning experience. So it takes a while to compile a kernel. So I had a lot of coffee then. So the thing is, coming back to my master plan, and my main point is that by the time I got to my application itself, I'd already gone through so many twists and turns trying to get all the other components to work, which was supposed to be the really easy part, because I wanted to do research on top of that. So up until this point, I was just setting up the environment so that I could do my research, which is quite interesting. So then I got a test bed set up, and I had a couple of computers, laptops from my coworkers. I had these little Intel NUCs, so these little computing like devices. I had 2 Nokia airframes, which are these like servers that Nokia has, and even a Raspberry Pi. All of these had a TPM, so I had my attestation server that was monitoring them, and it was a very nice test bed, basically, because it was under my control. At this point, I was doing proof of concept code. I was dealing with myself, my code, my mistakes, and I didn't have to interact with that many other people. But the thing is, once I did my research and I found useful information, I want to share this with the world. I don't want my research to stay in a documentation or in a paper saying, yes, this is really good, trust me. I would like to see people using it. So then we contacted the business units, and we got a product to say, okay, we'll include your proof of concept as a proof of concept feature in our product, which was great, very exciting. Another thing is that they let us access, so right now I had 2 servers, access to only 2 servers. They gave us a very nice test bed where we had 15 of these servers. I could play around with them. Bad thing, board hardware has an expiration date. So I was working against the clock. I had a new platform. They were using a different operating system, so I had to go again through all these challenges, albeit in a very, in an easier way, because I had learned from my mistakes. But ultimately, somebody came at the end and said, well, your time is up. We're taking the machines away. So during this time, another thing I learned was that when you're testing things in your machine, and notice that I was working with boot time measurement. So this involved, like I had to reboot the machines quite often because I wanted to try, so if I change something, will my measurements change? And that's quite easy in your own laptop because your laptop doesn't take very long to reboot. But servers take really long to reboot. So I had the longest coffee breaks ever. So it's right at the time that it's not long enough that you can go and do something else, but it's not short enough that you could just wait until it's done. So I had to also plan my time so that maybe I did the testing at the end of the day, so that it didn't interrupt my actual working hours doing productive stuff. So, and this is because server class hardware, if the fan fails on your laptop, it's not as bad, but if you have server class hardware, they do all this kind of self-testing. So when they boot up, they have to test the fans, they have to test the drives, they have to test like all the components on board before they can run, and that takes really long time. I think at some point it was taking 15 to 20 minutes every time I wanted to reboot a server, which was a bit crazy. And then another thing I learned was, as I said before, I was working proof of concept for myself, by myself, so my code was full of scripts and hard-coded paths because I had been working in an environment I controlled. But then that doesn't really work well when you want to share with others and when you want other people to actually understand what you're doing. So of course, to my eyes, everything was clear as day. I had self-documenting code. Not to the eyes of the business unit people. So I had to learn something I didn't sign up I didn't know when I started doing this project. I had to learn how to document, and I used actually that Sphinx. What is it? Framework for documenting. I think there was a talk about Sphinx yesterday, and I also learned about packaging. So one thing is, as I said, I had to deploy my proof of concept quite fast because the servers were going to be taken away, and I wanted to do testing on them. So one thing I did is, I had to move all my code base so it would be nicely distributed in packages. So, and I set up this Python index so I could do pip install proof of concept. And again, if I had stayed just at my little research by myself with my scripts, I wouldn't have learned all these things. So actually going out to the business units gave me this learning opportunity. It was quite nice. So once I had managed to write my proof of concept, I had managed to test on some other people's hardware as well. I realized that the standards in the real world, they don't always get along. So as I said, I was working with trusted computing, which is defined by the trusted computing group. So there's a lot of standards that say what you must do, what you should do, what you may do. And if you remember that little piece of code I talked about earlier, the CRTM, it's supposed to be the same piece of code. So I had 5 servers, 5 Nokia airframes, all the same kind of server down to every piece of hardware in there, identical in every single way. But then I took measurements of the CRTM, and one of them was different. And then I realized, well, what do our results mean? What is going on? Then I realized I don't really understand what is being measured. So it turns out that when you have your firmware supplier, so fortunately for us, we know who our firmware supplier is, and we can go and ask, so how is your CRTM behaving? What does your BIOS do, or your UEFI code? You go all the way back to your firmware supplier, and it turns out that it might be so that firmware makes the complete version of the firmware, but it gets sent elsewhere where it's installed on the hardware that you get, and it gets customized. So you might end up with a customized version of what the original vendor did. So then you start getting into this research into the supply chain, because the only way of explaining what you're seeing on your machines, again, I think it's because trusted computing is not that widely used right now. People are not asking for it. So once we start asking about it, I hope that pushing for this will make vendors now more standardized. So vendors could get away with just doing the bare minimum from the standard, and it made it very confusing as a user to figure out what was going on in my system. So are my machines trusted or not? And well, I must say there is a limit to trust. So I can only go as far as the firmware supplier. I have to trust them. So if they are giving me malicious code, it's a different area. My research in trusted computing, it's limited to the status of your platform, assuming you have a trust anchor at that level, at the hardware level with the TPM, with the CRTM code, and that you're using this DCG compliant BIOSes. But as I said before, one concern for the future is there's all these supply chain attacks. So what happens if an unknown third party tampers with the firmware? And that's when you have to start engaging in discussions with your suppliers and have to start getting them into higher. You have to check if you trust them or not. And I don't really know how to secure this part of the system yet. But then again, that would never happen, right? So in order to conclude, what I want to say is I hope you can get something out of this. What I wanted to share with you was how at the beginning I had this very tiny project. I thought, well, I'm going to do a Python project, little server. It's going to talk to some piece of hardware. And then it ended up taking me so many different ways, and I learned so many other things. So I find it quite amazing how I learned all these other skills along the way that I maybe wouldn't have thought I would learn. And this actually kickstarted now I'm going a career as a security researcher. So I would encourage you to go and challenge yourself and try these obscure pieces of code and hardware. And I hope you get something out of this. Thank you very much.
Thank you very much. Do we have any questions? Okay, we have one.
It may seem a bit obvious, but do you have an idea how to trust your attestation server?
How to trust my attestation server? Yes. So, of course, I can include all the details in this presentation, but if you have... So my attestation server is a piece of Python code that I'm running somewhere. If I'm running that piece of Python code in a trusted machine and I have all this things set up with IMA, one thing I was doing is that I was measuring my Python code with IMA, storing those measurements in one of the BCRs, so that if anyone tampered with the code of my attestation server, I would know. And furthermore, there's this TPMs. You can also, the things you store in the RAM, you can seal them against the state of the PCRs. So I would save all the configuration. Sorry, if I'm going too fast, let me know.
That's fine.
Yeah, okay. So I would seal the configuration I needed for my attestation server in NVRAM so that it could only be used if the attestation server had not been tampered with.
Then again, it boils down to the root of trust.
Yes.
You have to trust your firmware on the attestation server itself.
Yes.
And for this, I think the only way to actually trust the firmware is to compile it yourself.
Yeah.
It's the kind of the only way available right now, like going core boot.
Yeah, it might be so, but then the thing is, so
you can be sure if you want inspect the source code that you're compiling.
Exactly.
So the thing is, at least the way I was working with is in the cloud, so you're not gonna, Nokia doesn't do its own firmware, but you know the vendors, so you go and talk to them, and I think they have to provide us, or they can provide us their source code if we ask for it. So then it's starting pushing this trust investigation a bit further back, as I said at the end of the slide.
Yes, but then if they provide the source code,
yeah,
how do you actually verify that the compiled code that lands on the machines is actually derived from the source code, or maybe hasn't the compiler been tampered with? It's still possible.
Yeah.
Okay, but
yeah,
that's just an idea. Thank you.
Yeah, thank you.
Okay, thank you very much. I'm seeing better from this place. So do we have any other questions?
I think, yeah.
Hello, great talk, thank you. But so I'm interested, how much time did it take you to realize all this plan? Since you started with small Python project.
Yes, so I started working on this in January, and I roughly finished the current version I have right now, I would say sometime around August or September. So a bit of an incremental process. So.
Are you going to take it to open source, or it's internal Nokia product?
Right now it's not at the state that we can open source it yet, and I think there's IPR issues, so as soon as those are figured out, I think we would like to take it open source, but it needs to be, so right now the proof of concept level, maybe the code needs to be made a bit better and harder than these other more productized worries about code. So I wouldn't open source it as it is right now, but I think that would be a plan, because there is one competing product, I think Intel has an attestation server that hasn't been updated since 2016. I think they kind of let the project die. So I think it would be good to have an alternative somewhere.
Thank you.
Thank you.